Hi, my name is Colin Gensch. I'm the CEO of Retrotec, and I think Joe Medish was supposed to be doing this webinar today, but unfortunately he's at a trade show, and I'm going to be filling in for him, and hopefully I can shed some light on some issues for you. So we'll just give everybody a moment to settle in and get yourself a cup of coffee. We've got a lot of people on the line, like I say, from all over. We've got roughly around 20% of the people from Europe, 80% of the people from North America, probably 70% from the United States, and another, say, 10% from Canada. So I've decided that I'm going to do only imperial units here. I know that's kind of a faux pas when it comes to Passive House, but I just started on imperial units. The principles are exactly the same. There's nothing really different. This stuff is not particularly unit sensitive. What's cool about the door fan measurement values that we make Airchanges is, apart from the pascals, which we all use, it's almost a unitless measurement just per hour. So it's the same no matter whether you're measuring flow in CFM or cubic meters per hour or whatever, liters per second. 0.6 Airchanges is based on the volume of the house, and we'll get into that in a moment and describe that. We're going to start with talking about Airchanges. So a little bit of math for you, not complicated math, but math nevertheless. So what the heck is an Airchange at 50 pascals? Well, Passive House requirement is 0.6 Airchanges per hour at 50 pascals. And what that means that when we test the house at an artificial test pressure of 50 pascals, that it should be no more than 0.6 Airchanges per hour. So one Airchange would be one whole house volume. 0.6 Airchanges is 0.6 of a house volume. So in this case, if we got a 2,000 square foot home, 10 feet high, the volume is 20,000 cubic feet. So 0.6 Airchanges is 0.6 times 20,000, which is 12,000 cubic feet per hour. We divide that by 60 and we get 200 cubic feet per minute. So for this particular house, what we're looking for is a flow rate of 200 cubic feet per minute at 50 pascals, and we are going to be testing in both directions here to get more accurate results, which really has very little to do with how much air will flow in and out of the home under natural conditions, which we will touch on. There are some rules of thumb that we can apply to Airchanges at 50 that will convert those values to natural Airchanges. And a very common number that's used is 20. So in this case, 200 CFM at 50 pascals, we divide that by 20, and that's roughly about 10 cubic feet per minute under natural conditions. And that depends on the exposure of the building and various other things. But we will convert this number into a natural Airchange rate later. But before we do that, we're going to cover some simple stuff. So this Airchange rate can either be done by running a complete test and taking a whole series of data points, or simply taking out your equipment, turning it on, and taking a reading. So here we have the output of our fantastic software, which you would set up to take a whole series of points, and you're basically talking about half an hour of testing, or you simply turn your gauge on, as we've done over here. You adjust the fan speed, either manually or whatever, to 50 pascals, and this particular gauge is designed to read out directly in Airchanges per hour. This is probably the second choice, would not be how you would say test the home for certification purposes, but you might be at a certain stage of construction. You say, well, gee, I wonder what air change rate we're down to at this point. Turn on your fan, and in 5 seconds you can get the air change rate. This gauge is cool because it has a feature on there that allows you to put in the volume, and when you put in the volume, I just drag it over here. There we go. This is actually a virtual gauge, which simulates a real gauge and works in the same fashion. So in this case, we can change CFM to air changes. We change units to air changes, we put in the volume, and it reads out in air changes. Simple as that. And there's the virtual gauge. Just reminded me to take a look at the virtual gauge. It's a great little learning tool. It's free download from our website. Okay, I'm going to get into measuring volume in a minute. Test equipment. There's a variety of test equipment out there. This very modern looking device was one of the first duct testers that I was involved in designing back in the 80s, and it was designed for CMHC research division, who's been responsible for a lot of the building science that we use, North American, even worldwide, was funded by the Canadian government, who then got more interested in selling oil. But nevertheless, they did design the first duct tester, and this one was called the Duct Test Rig. I think they built two, and I think one might be in the Smithsonian, I'm not sure. But the reason why I show this is that it's basically a small blower door fan, and these houses are tight enough that we can use these small fans to depressurize the entire building. So later incarnations, as this evolved, you can see it's evolving from square and smaller and evolving to a little smoother and cooler looking, and we have another evolution coming out soon. The other evolution that we've attached to this is we've designed a door frame. This is unique, where the corners aren't mitered, and there's a molded piece in the corner, and it goes right into the corner of the doorway. So the passive house folks were complaining that the aluminum frame was leaking out the corners, these little teeny weeny holes about the size of a pencil in each one of the corners, because the miters didn't come together square and the weather strip didn't go to the corners. This particular unit, the weather strip actually goes all the way out to the corners, and it's quite a cool little device. So that's a Model 241. This is one of our new wireless gauges, which is not really necessary, but would allow you, say, if you were doing air leakage control in your passive house, to be in a certain part of the house, and you could just touch the keypad. It would immediately tell you what the air change rate was, or it would tell you, what kind of a reduction you got in air leakage from the last measures that you did. So kind of a cool little thing, not necessary, but kind of a nice little techie device that can save a little bit of labor. I think Joe came up with that slide and he said, work smarter, not harder. I'm sure that most of us are working harder and smarter. This is another new device that has been, I would say, recently developed, except the company that's developed it's been working on it for 6 or 7 years and put a huge amount of R&D into it, and we feel it's the best device made for its purpose, and it's called the Flow Finder Mark II. And it is by far the most accurate flow measurement device that you can get when you're measuring HRVs or ERVs. And on the right-hand side, you can see it packed in its case with various flow hoods. As I'll point out later, the whole main body only weighs 5 pounds. You can hold it in one hand, and you can measure supplies and exhaust with the same device. So super accurate. They are expensive, but they're worth every penny. So let's take a look at volume measurement. In a recent comparison study, or a relatively simple, straightforward building, We got 6 extremely experienced testers, I mean the best of the best, and they went in there and they measured the both the volume and the enclosure area of a fairly straightforward building, and the variation in their volume was, I think, in the neighborhood of plus minus 5%. So between the highest and the lowest, we're talking 10%. And when we're measuring air change rates, our air change rate calculation is directly dependent upon the volume. So since I brought that up, I'll just drag a spreadsheet, hopefully. I'm just going to drag a spreadsheet over to the screen here, if Microsoft will cooperate for a moment. And let's just kind of expand this out here a little bit so you'd have an easier time seeing it. There we go. We'll just expand those fonts there. Now it looks like you can see that. So you'll notice here that here we've got a volume. We air changes at 50 pascals of 0.6. I've converted that into CFM and so on. So clearly, when we change this volume here, the air change rate will move in direct proportion to it. So see if I can demonstrate that on my virtual gauge over here. So unfortunately, this air change rate's 0.3, so we don't have enough resolution. So what I'm going to do is I'm going to change this to 2,000, so we'll have a bigger number to play with, and I'm going to change that by 10%. So 2,000, 10% of that is 200, so I'm going to change that to 1,800 volume, and we can see the air change rate immediately changed. So it went from 3.05 to 3.39, so the air change rate changed in direct relationship to the volume that we just changed. So it's important to understand those relationships, and when we do, we realize that the volume measurement is an important value. So the volume measurement that we're looking for in this case is the occupied volume of the building, and of course there's going to be all kinds of convolutions and so on in the building that are going to affect the actual volume that this building has. I guess the best way to measure the volume would be to fill it up full of water and then drain the water out and measure the volume of water. Unfortunately, that's a bit messy and time-consuming and would probably destroy the building, but would probably be very accurate unless it leaked. Okay, so I'm going to move on. I've already mentioned the 10% variation in volume measurement. So now we're going to talk a little bit about setup and preparation. The idea of any air leakage measurement is to determine a value that will either indicate the performance of the building overall or the performance of particular components of the building. So in this case, when we're doing air changes at 50 and so on, we're really looking at the performance of the building overall. So that means that intentional openings such as HRV vents, exhaust fans, ventilation openings and so on aren't taken into account because we're trying to see how tight can the building be under normal operating conditions. So the way I look at any exhaust or supply flow devices, I don't look at it as being a hole because it doesn't act as a hole. I look at it as being a flow that's going into or out of the building and not really a hole. Unlike, say, an intermittent exhaust fan that is open 99% of its lifetime and with the fan not running, it's basically a hole in the enclosure, and the hole affects the performance of the building. So it spends 99% of its life as a hole and 1% of its life as a flow device. So that's quite different from a continuous ventilation device, which we really won't be looking at as a whole. So in terms of the building, we're going to be sealing off all of these openings, and there's a number of techniques that can be used in doing that, and I won't get into it, but suffice it to say that when you're getting down to the tightness level that's required for these at 0.6 air changes per hour at 50 pascals, even minute little pinholes, not quite pinholes, but say nail holes, can actually make a difference. So you will be testing the intentional openings in the same fashion that you'll be testing the building, because if you don't seal the intentional openings properly, they will be measured as if they're unintentional, and it's going to affect your overall result. So it's really a matter of experimentation and the use of air leakage devices that we'll show you later to find out how they should be set up. The one other important point that may not be completely obvious is that whatever preparations that you make to the building for the air leakage test, you have to document them, both to document how you did the test, but also when you leave, you've got to remove your temporary air sealing so that the building can still function. And it's a really common thing for someone to do a test on someone's building and then to get a call back to say, well, this or that's not working anymore. So that's a warning. So I'm going to talk about some testing problems that we're going to face, and one of the biggest ones is exposure to wind. And there, I would say that the most important thing we can do is the outside pressure tap should be on the downwind side, and a lot of the manuals show spreading 4 tubes around the building and so on. That helps to a certain extent, but what I find is often I just put 1 tube outside. If I see more than a 1 or 2 pascal fluctuation in the pressure, it's called the baseline, I'll put a T on the end of that, and I'll run 2 tubes on there that are roughly about 15 feet long, and I'll pick up pressure at 2 different points, hopefully still downwind, and a few feet away from the building. And so the proof of your effectiveness of your pressure pickup system is whether or not you're getting fluctuations. So you may have to manipulate them to a certain extent for a certain period of time until you're happy with them. If the wind is not blowing, just throwing a tube outside will give you fine results as long as the fan is not blowing on the tube. I also like to put, say, a piece of 1/4-inch plywood, 1 foot by 1 foot, 2 foot by 2 foot over top of the tubes if there's any wind, so it keeps the wind from blowing into the tubes. That works better than the old trick of sticking it in a Coke bottle. The other thing is, if you look very carefully in this picture, you'll notice there's a drop of water in there. If there's any rain around there whatsoever, you touch the end of the tube to that water and it will immediately seal the end of that tube off. So this is what a windy day looks like. This is 10-second averaging. You can reduce that by using longer-term averaging that can happen both in the software and or in the gauge. Just because you put averaging in the gauge, it doesn't mean that that averaging will extend to the software. So the software averaging does its own averaging, and the gauge averaging does its own averaging. And you can see here that we've gone from like 0 down to about -5, which is, for testing at 50 pascals, that's fully 10%. We're doing a multi-point test and going down to, let's say, 15. That's going to affect our results massively. Today, wind is blowing roughly about 20 miles an hour. So when we compare, let's say, 10-second averaging to 60-second averaging, this is a whole series of points that are taken with 10-second averaging. I think around 550 of them, and this shows the variation in points that we're getting. Actually 15 pascals. When we go to 60-second averaging, you can see how that shrinks down dramatically, and up at 50 pascals, you don't see it so much, but you'll notice how these lines narrow up, and we get results in a tighter band. So let's take a look at using blower door values of the N and C. First of all, we're going to drag our software onto the screen to see how we get N and C, and then I'll describe what it is. I've got another slide here that demonstrates an important point, and that is that if we have a hole in a sheet of 1/4 inch plywood, 12 inches by 12 inches, and we measure that hole at 10 pascals, 50 pascals, 500 pascals, it will measure 144 square inches in all of those situations. If we have a laminar flow device, which is a tube that has a series of what's essentially little tiny cracks, 1/100th of an inch diameter holes that are about a foot long in it, and we measure that at, let's say, 10 pascals, and then we measure it at 50 pascals, we find that the leakage area seems to be increasing as the pressure goes up. The hole's not getting any bigger, it's just that the relationship between pressure and flow has changed. So here we've got what's called an N value of 0.5, and we've got 257 square inches at 10 pascals. We've got 257 square inches at 120 pascals. This is a hole in a flat plate. This is more typical of the kind of holes that you get when you're testing a passive house. You're going to expect to get an N value of 0.7, and the reason for that is a combination of holes in a flat plate, which are just holes, big holes, and little tiny cracks where the air will go in between two surfaces, and the flow between those surfaces, because they're together, will be laminar. Laminar means one molecule behind the other as opposed to turbulent. So the relationship for area, N equals 0.5, is square root. The relationship for laminar flow is area is equal to flow divided by pressure times some constant. No square root at all. Okay, when we get a combination of those two together, then we get an N value that's somewhere between 0.5 and 0.71. Fortunately, the software does all this for you, so you don't have to worry about it, but you do have to know what it means, because once you make a measurement on your house and you get an N value of 0.5, what does that mean? You've got a few big holes, you may even be able to stick your finger or your hand through them. So that will tell you what kind of leaks that your building has and what kind of leaks you want to look for. The other thing, while I remember it, is we'll just drag this over to the screen again. Air change rates are fine, but they're hard to visualize. So one really cool way to visualize them is to visualize them in terms of EQLA, and we'll just put this in square inches. So in this, we're talking about 10.5 square inches. Now that's not 10.5 inches square, but 10.5 square inches, which is 10.5 inches long by 1 inch high. So basically about the area of a typical ruler. So that's the size of hole that you're looking for in the building, with all the holes added up and stuck in one place and characterized by the equivalent hole in a flat plate. So if you were to measure a hole in a flat plate in this building, they would measure exactly the same value in terms of equivalent leakage area. So leakage area is something that you can look in your software. It will tell you what the leakage area is. But long before that, you probably would have done a series of measurements using your gauge and just looking at the area in order to find out what the leaks are. We'll just drag that off the screen here again. I think this would be a good time to look at the software. So in this case, I'm using Fantastic, and with Fantastic, I was hoping that I had a the file. All you need to do is find the file and click on it, and Fantastic opens up. But this is not really an exercise in how to use Fantastic. There's a great manual on it. We've got videos on it, so on, and we've had other webinars on it. So it's not about that. It's just about the results. So here we have the software. Well, it's mounted up to full screen here. And I won't bore you with going over the details of the building. In this case, ASTM E779-10. I think possibly in Europe you'd want to be using the European norm or the ISO standards in that case. Under Tools, Advanced Options. I can never find this. Fortunately, in the next version, we've changed its location. So here we go. So in here, we have the choice of running ASTM, CGSB, European norm, which is essentially the ISO standard. We've got the European version, Belgium, Denmark, France, Sweden, all that stuff. One of these will be the standard that you will be doing your final blower door test to. So I've got this set right now on the ASTM standard. So we'll just wrap that piece up. In case you didn't see that, I took the application info there and I just made it disappear, and I still see the important information on this line. This is about our equipment. We can get rid of that. These are building details, heights, volumes, and so on. In this case, we've put in the enclosure area at 20,000 cubic feet, so we can roll that up. I'm hoping that you're able to see this screen with enough resolution so it makes sense. And if for some reason you can't, let me know and I'll spend a lot less time on it. But the most accurate way to do a final test on a building is to test it pressurized and depressurized. It gets rid of a ton of errors and so on. It gives you much better readings, and most baselines drop out and all kinds of good things happen. So in this case, we've done a pressurization test. We don't even have to tell the software we're doing a pressurization test. All we really have to do is to put it in an automatic mode and press go, and it will do the test according to the ASTM standard. But beside that particular point, what we've done here is a pressurization test, and I've just put some values in here. We've tested them from 50 down to 15. We've got a result, and you can see over here we've got an air change rate of 0.6085 at 50 pascals, and that's really the only number that we really need to know. But the other one that we've got down over here is we've got the exponent, the n value of 0.5527, and we've got the C value here of 23.4, and the units here are CFM. So these are the values that we need to do some calculations. Once we know those values, we know everything about this building in terms of how it leaks. So we did this pressurized, and we hit calculate, and we got these results. Then we asked for a new set over here. We did a depressurization test that you'll notice is minus, and we got another result. And in the software, when you test minus and plus, or depressure or pressurize, the results will be averaged. And that's exactly what's happened here. So this is our depressurization set. I'm just jumping over the infiltration analysis here momentarily. And here we see the two of them averaged. So we now have an average of those two as far as results are concerned. And there they are. Sometimes I stop talking like that just to make a note. Doesn't mean that I've disappeared. In some cases, when you test according to one standard or another standard, you'll get very different results. And the reason for that is that different standards are designed to yield different results. The ASTM standard is a very general standard, and it actually doesn't really focus on results in any particular direction. It was actually designed for getting EFLA at 4 pascals, but it's also a general standard that allows you to get results at 4 pascals, 10 pascals, 25 pascals, 75 pascals. You can divide those by area, by volume, by whatever. So there's a lot of very different results in here. So that's what the software looks like. So having said that, we can jump out of the and go back to taking a look at what these values mean. So I've written those values down, and we're going to be using them later. I'll be explaining what they mean later. Okay. Let's just take a look at my slides here. Natural infiltration. Okay, before we get into natural infiltration, we'll just back up a little bit, and we will take a look at our spreadsheet, and we'll play around a little bit with N and C. So N value is 0.5527. C value is 23.40. So from a mathematical standpoint, what we need to do to get CFM is to do this. We have pressure that we're interested in, so the pressure is here, and the CFM will be over there. Okay, so if we want a pressure of, let's say, 50 pascals, and we want to know what the CFM is, then we go, CFM is equal to 50 pascals, and this is the power sign. This is the little roof that's above the 6. So I go shift 6, which gives me that little roof there. It's taking it to that power, and then times this constant 23.4. So you'll notice here, I'm just going to get rid of all this gooble gobble on the end here. 203 cubic feet per minute. So essentially what that's saying is if you apply a 50 pascal pressure to this building, it'll take 203 CFM to do that. Well, we know that because when we did the test, that's exactly what we did. Let's just drag our test back and take a look. Oh, where'd it go? Come on. Clicked on the wrong thing. Here we go. So at 50 pascals, what we did is we just entered CFM in here directly, just as if we read it off the gauge. So kept it simple. So we said that we measured at 50 pascals, 202 in this case CFM in the depressurization direction, 200 CFM in the pressurization direction. So these are the values that we used in order to measure the leakage in the first place. So we might ask ourselves, well, what happens if, like how much flow would it take to create 1 pascal pressure? Okay. So we take the same equation here, we'll just copy it, paste it on that line, and let's see how much flow it will take to get 1 pascal, 23 CFM. So you'll notice this is changed by a factor of 50, but this is only changed by a factor of about 9. That's that power function, or the square root. It's not quite a square root, but that's the power function happening in there. So the first pascal of pressure requires a lot more flow than the next pascal of pressure. And to prove that to ourselves, we can say, well, let's just put 49 in here. So here there's only 2 CFM difference between here and here, and we change 1 pascal. Here from 0 to 1 pascal took 23 CFM. So obviously the first pascals are taking a lot more pressure. And that's because you take the square root of 1 is take the square root of 100, it's 100. So one's a ratio of 10 to 1, the other's a ratio of 100 to 1. So these N value things can really kind of shake you up a little bit. So this little formula would be useful, let's say, for example, if we had an imbalance in our HVAC or our ERV, for example. So an imbalance in our ERV of 23 CFM will produce a 1 pascal pressure in the building. Not really the end of the world, but you can see it actually takes a fair bit. If we were concerned about how much pressure it would take to get, let's say, a 4 pascal pressure in the building, yeah, we're up to around 50 CFM, which is getting kind of substantial. 4 pascals is not the end of the world, but it does take a fairly big imbalance of pressures to get those initial pascals up. So Andy was saying, give us the CFM formula. So there's 2 CFM formulas that you need to know. One is that when we're measuring a hole, then say a hole in a flat plate, for example, we don't know like what kind of hole it is. Then we say that CFM is equal to the area in square inches times the square root of the pressure times 1.075. So this is the flow formula for the flow through a hole in a flat plate. The formula that we use down here, which we can bring up, I guess that's kind of hard to see, says that CFM is equal to pressure to the N power times C. You don't really have to know those, but those engineering folks among you won't have any problem with these formulas. All these formulas are taken care of inside gauges and inside software. So all you need to do is like pump in the numbers and you'll get the results. But if you really need to know, that's where they come from. So I'm going to move along here to natural air change rate. So let's drag the software up again and try to get an idea what the natural air change rate is. Remember earlier that we took the air change rate at 50 pascals and we divided it by 20, and we got 10 CFM. 200 CFM at 50, 10 CFM under some kind of natural conditions. That's just kind of like the easy way or the rule of thumb way to convert flow at 50 to natural flow rates. So that rule of thumb gave us about 10 CFM. And that factor of 20 will vary anywhere from about 25 down to 10, depending on the exposure of the building, the climate, the average wind speeds, the average temperatures, all kinds of numbers. And there's papers written on that specific topic. However, a much more in-depth and accurate analysis is provided in the software here, and it's done under, let's just get rid of this, get rid of that, get rid of that. So all we've got here is the infiltration effects, okay? So in this case, we've chosen Seattle climate data, heating with electricity, or cooling with electricity, or maybe not. 1-story high, 4 bedrooms, heating 10 cents a kilowatt hour, $0.1, 100% efficiency, cooling cost, same thing, 14 SEER. Winter design, summer design, this is pulled in from the climate data. You can enter your own if you want to. The shielding, which affects the air change rates. And you'll see here that we have a winter design natural air change rate of 0.04 air changes, 0.02 air changes, and this is for a house that has a little bit over the passive house standard, and we're worked out on about 12.5 CFM total average natural infiltration rate over the entire year. 24 hours a day over the year, and using the old 20 factor we came up with 10, so that was a bit on the high side. If you looked it up in your table, there's a table that shows you the real factor to use. It might have been a little closer, so they're in the same ballpark. So 12.5 CFM is not really enough for people, so obviously this house is going to rely on continual ventilation from the vent from your ERV or HRV or whatever it is. I think I've covered all of the inputs here. So this is saying the required ventilation based on, I think this is the ASHRAE standard of around 15 CFM per person, is that we need 57.5 CFM if we base it on 24 hours. Obviously, if we change it to 12 hours, it doubles, and so on. So usually with ventilation rates, they tend to build up over fairly long periods of time, and as long as you get your average daily ventilation rate, then it seems to work out fine. There's a certain amount of internal pollutant loading that you can get. It's obviously better to ventilate more when there's more people in the house and there's more activities and so on. So there's some variables there, but there is a certain amount of momentum in the air change in a building. The air doesn't go bad immediately the moment 4 people show up. So this ventilation can occur over a prolonged period of time. The other thing I wanted to show you down here, which is really cool or hot, is that their infiltration cost for a year is $18.43. So this is the natural infiltration rate based on 0.6. I know a lot of these houses are getting down to 0.3 and lower, so we can say that the losses due to infiltration have virtually hit zero. Now this heating cost for the year due to conductive losses and everything else, this is infiltration part only. So this is only the infiltration analysis. On the cooling side, 5 cents. So people in Seattle don't put on their air conditioners very often. Change the climate zone to go to, let's say, Edmonton, for example. Whoop. We'll notice that the cost of that infiltration has jumped up dramatically. What's that, about 4 times or so? Obviously, much colder climate, no particular cooling load. You know, we were to go to, say, a different Lubbock, Texas, a little bit on the cooling side, so between the two on the heating side, so you can have fun with that. Okay, so that's the info analysis. So we're actually only at 4 minutes, and I've got a huge amount of material to cover, I think, but I'm going to touch on locating and sealing leaks, because that is a much bigger job than actually measuring. Measuring these buildings is dead easy. Getting them tight and finding the leaks is really hard. So let's just take a look at that. So it's true that most of the leakage is at the top and the bottom of the building, and those are the leaks also that usually cause most of the energy loss, because the stack is greatest at the top and the bottom of the building, and but it's where the vertical surfaces meet the horizontal surfaces that you're most likely to find the leaks. So just in a very general sense, that's where you should be looking. And also, whenever you have a change in materials from, say, foundation materials to the framing, walls, whatever, those are also the places where you get a lot of leaks. And whenever there is any kind of penetration in the envelope for anything, there's usually a lot of leaks around there as well. So that's not really the only thing about finding leaks, but just some basics that found over the years. So penetration in the envelope also relate to windows and door frames and so on, where you've got a discontinuity. So when you're transitioning from a window into a wall section, those are the areas that we'll focus on, and all of you who've been in this business, I'm sure you know that. So here are some techniques that we use. Now, the one in the middle, which is, it's not my hand, but someone's, is actually one of the best leak detectors we have for finding reasonably large leaks very quickly. So on the initial stages, when you do your first go-rounds, you want to find out where those big holes are. One of the reasons why we talked about equivalent leakage area was to give you a visual clue as to how big a hole that we're looking for here, and around about 10 square inches, okay? So what we would typically do, and to sensitize the hand, I like to use a little bit of rubbing alcohol, or vodka will work as well, but you might have a better use for that. Water if you don't have anything else. Really improves the sensitivity of the hand to airflow, done from the inside, of course, and done on a negative pressure of -25 if you can get it. If you don't happen to have a blower door or something to depressurize the building, you can try and depressurize the building with the exhaust devices, and just to get that negative pressure inside the building so you can walk around the kitchen cabinets in various areas and just be looking for those holes. So that would be your first run through, would be with the old wet hand technique. Once you get that done and you want to look at individual components, then we would use a smoke like this, which is a neutral buoyancy smoke, titanium tetrachloride, unfortunately a little on the caustic side, and since 9/11, one that's impossibly difficult to ship. If you ship this, you have to ship it under a hazardous materials designation, and if you don't, you can be fined horribly. So I would suggest that if you buy these, that you do take that into account. But one great thing about this kind of burn tester or smoke puffer is that it will detect pinhole leaks. You need to get really close to the item and put a tiny amount of smoke in there, like a cubic centimeter, a 1/4 by 1/4 inch blob, you know, a little tiny bit, about the size of a pencil eraser. That's all the smoke you need to test an individual component. And if that is leaking, if you can see this picture here, the smoke will snake into that hole and identify it. Now here we show someone using a theatrical fogger, which I don't think has as much application in super tight houses as it will in real leaky houses. It's based on a heated oil, and there is a little bit of oil that condenses out from this. It is a safer smoke. It's the same smoke that they have at rock concerts and so on, or plays or theater and so forth. And then the next, of course, is infrared, and we can depressurize. I'll probably show you the next slide here. This is the theatrical smoke. Will not really recommend. If you ever use this stuff, by all means, call the fire department before and tell them what you're doing. Otherwise, they'll come down there and try to put it out. Here we are, some infrared shots. So this is a building from Northern Europe under normal conditions, and infrared under normal conditions. Can't see a heck of a lot. The moment we turn on the blower door, and in this case depressurize to -8 pascals only, then all of a sudden, whoa, the leaks show up incredibly. Here what we've done is we've done a flow reversal. We've sucked the cold air into the upper leaks before the warm air was leaking out through the upper leaks, and really making them very, very hard to see. So the moment we use the blower door, it supercharges your infrared, and all of the best trainers on the infrared side strongly recommend that you use some kind of depressurization device from inside when using infrared, and a pressurization device blowing air into the building when you're looking at the building from outside. So great diagnostic tool. And here we show, this is without blower door fan, this is with blower door fan on a different, this is a roof section. So here we show the air current tester. We been making these for 30-some years, and have heard stories of woe of people that have destroyed their computer or their gauges because they will corrode metal. The tool cases that we sell have a vented pocket on the outside so that when the smoke puffer leaks, and it's not a matter of if, it's a matter of when, it leaks, it's not going to affect the contents of the bag that could be your computer, could be your camera, could be your gauge, could cost you thousands. So if you learn nothing else from today, learn to keep those two separated because they hate each other. So as far as sealing air leakage sites, one of the most important tools that we have in our arsenal for measuring our effectiveness is to be doing continuous blower-door readings as we're going. And you don't have to run any kind of fancy software. All you need to do is to bring up your gauge and take a reading. And I suggest that when you're doing leak location that you do it in EQLA so that you know what size of hole you're looking for. You can easily just click on this and change it to air change rate anytime you like, and you can flick back and forth. Super easy. But if you were to, let's say, do a whole course of ear sealing on the top part of the building, and you do it before and after, then you can see, well, we did this and this and this and it had no effect. We did this and whoa, it went down by 40. So this is the greatest learning tool that you have. The devices we just talked about told you how to find the leaks. This is telling you how to quantify the effectiveness of the leaks. You might find a leak, a crack that's 20 feet long, and you can see smoke going into it to the entire length. You seal it and you remeasure and you see no difference. Or you might find, say, some kind of plumbing stack or something, you foam it, and the leakage might go down by 15–20%. This is really important information. Just because you put a lot of caulking material and so on, and you seal a lot of cracks that appear to be leaking, doesn't mean you've actually found the leaks. So your blower door or whatever you happen to be using to measure the air leakage of your enclosure, a really important function it has is to teach you how different components are leaking and the effectiveness of your air sealing measures. Now the next thing is to, this is getting away from the enclosure leakage, and I'm sorry I've already gone over time by 8 minutes, but so many exciting things to talk about that I guess we needed the time. The ERV flow rates are most accurately measured, again, with a device like this. Now, the simplest possible thing is, if you got nothing else, you take a box, you slap it over your inlets and your outlets, you stick a gauge on it, and you measure the flow rate. These things, even though they look inexpensive, and actually they are, actually measure exhaust flows pretty well, but almost nothing measures supply flows well. So if you use a device like this, you could probably accurately measure your exhaust flows to within easily 10%, maybe even better, no problem at all. If you measure supply flows, you could easily be up by 40–50%. Those same errors, maybe not quite as bad, are applied to most passive devices. When we use one of these little puppies here, it measures supply flows with equal accuracy by virtue of a massive amount of research in order to solve the problems of what we call jetting, which is different velocities firing up into the device and making it very, very troublesome to measure. And the moment you try to measure the supply and exhaust of these devices, and you add supplies, and you add exhaust, and they differ by 30 or 40%, you realize how difficult it is to measure supply flows. And so that's what these devices are useful for. Cool thing about it, 5.5 pounds. There are various hoods. This one here is 8.5 inches. This is 16 inches, and so on. And you can see, quite easy to hold in one hand. It'll run all day on a battery charge. You have to buy batteries for it. Stores all the information right in the device if you'd like to. It'll show you values in CFM, cubic meters per per hour, liters per second, whatever you want. Now is measuring barometric, humidity, all that kind of cool stuff. So this is, as much as infrared has added to our toolkit and blower doors added to our toolkit, this is the third powerful device that will allow you to diagnose what the heck's going on in a building. So I'm going to sign off now. Great webinar. Thank you for attending. Sorry about the croaky voice, but that's the way it is sometimes. And we'll look forward to seeing you on the next webinar.